Hi, everyone. Welcome to today's masterclass on optimization techniques using MATLAB. Thanks for joining me today. This is the final webinar in the sequence of classes that I've been doing. My name is Loren Shure, and I've been at MathWorks for over 30 years. And I try to share my knowledge like I am today in various kinds of classes and talks. And you can see in the YouTube channel that there's a whole bunch more that I've done recently on interesting topics in MATLAB. You might find some more useful MATLAB tips as well on the blog that I maintain, The Art of MATLAB. And with that, let's get started with today's topic, which I said today is solving optimization problems. So let's come here. I'm going to start off in slides, and I will have slides throughout, but I promise you there will be MATLAB in the middle of all of this. So the outline is right here. I want to give you an introduction to start. Okay, so optimization problems. Optimization problems are pretty much everywhere if you think about it. If you think about it in terms of whether it's finance or business or engineering, we might want the most energy efficient thing. We might want the one that uses the least amount of fuel, something that heats something the least, whatever. Even in everyday, we're doing optimization all the time, although maybe not formally. For example, when I go outside of my home and I'm trying to get to the bank, I might decide that I want to go the fastest way I can. However, on a rainy day, I might not care about getting there the fastest. I might care about finding a way where I'm underneath some covering overhead so that I get the least wet. So I'm making different choices each time I do something like that. But I might be, on some days, I might not be optimizing anything. But some days, I'm making deliberate choices, even if I haven't solved the problem, to make sure I'm doing it the best way. So how does the design process work for optimization? Well, what we do is we typically get some initial design variables for whatever we're doing, and we put them through the system, and we look to see if the objectives are met. And if they are, yay, we have an optimal design. And if they're not, we go through and we modify some of the design variables, and we put them through the system, and we keep checking until we're close enough. Now, if we have a very modest number of these variables, we might have some intuition about how to change them. Oh, I want to be, I don't know, whatever. I clearly want to try to make the temperature lower. That's going to be more effective than one of the other things. I might have some insight like that. But if I have something like, 100 or 1,000 design variables, I might not have that same kind of intuition. And so how do we go about and think about these problems? Well, I'm going to show you an example just in slides here, and then I can show it to you for real, perhaps. But what you'll see here is I have plotted some engine efficiency contours here, which normally we wouldn't know. We wouldn't have mapped this whole thing out. So it's a treat in some ways that we have this part of the data set. But what you can see is that I have choices about how many revolutions per minute the engine's going to run and what the pressure ratio is. And remember, if I'm really doing the optimization, I usually can't see this picture underneath. So what do? Well, I take an initial guess, and I pick an initial direction to try to move in, and I move, and I go, oh, was that better? Yeah. Okay, if it was better, let me keep going that direction. Is it better? Yeah. Let me try again. Not better anymore. So let me come back, but let me come back partway. And I might iterate there a little bit. And then I look in the next dimension and I try to find the next appropriate setting. And then if you imagine if it's third, fourth, and fifth dimensions, which I can't easily show here, then we would be doing this in all of those dimensions. But what you see even in these two dimensions is that I'm not ending up in this area, which seems to be where the maximum is, and there might be a nearly as good a maximum somewhere in here. So this manual, even though I think I'm being sort of systematic, it's not working really well for me. So what would we do instead? Whoops, we might want to use some automatic techniques or optimization techniques. And in these techniques, many of them, but not all of them, are gradient based. So what we might do is take the same initial point and then kind of look around us and see which direction is the steepest way, in this case, up, because we're trying to maximize something. And I take a step in that direction, and then I look around me from where my surroundings in the new location and see which direction to go. And you can see as we do this, we ziggle-zaggle our way into a locally optimal spot. Perhaps not the globally optimal spot, but at least it's better than we had before. So why use optimization? Well, as you could see from my description, we have a chance of finding better or optimal designs or making better decisions because of that. It's probably letting the computer do some of this calculation. It's probably faster to do, not just because that it can do the calculation of what's the engine efficiency, but it can do those gradient estimates more systematically and more correctly than I probably can just by using my eyeball to figure it out. And that lets us automate routine decisions. If we know that this is what things always depend on, we can just say, well, just let it go. It doesn't really need me in the middle anymore once I've written down all the correct equations. Another thing you can do is once you get near an optimal solution, you can say, if I change variable 1, how much do I have to change it to get a certain percent change in my efficiency, let's say. And what if I change variable number 2 and variable number 3? In this way, you can find out sensitivity or trade-off analysis to see which one is more likely to be sensitive. And you might be able to back off one of the dimensions that's very expensive a little bit, enough to save money on that dimension, let's say, but not really hurt finding the best solution. And then finally, it's quite possible that you might find non-intuitive designs. And I think that that's one of the things that's delightful about this on top of everything else. What you'll see here is a picture of an antenna that NASA deployed, and they designed it using a genetic algorithm design. And what you see is what they ended up with. Now, they wanted to put this antenna on a payload going up to the space station, and then it needs to work up in the space station according to some specifications. And so they made sure that their optimization knew about the specifications, and they started it off with basically 6 prongs that were kind of evenly around a circle. And you'll notice what they ended up was this thing with all these bends and twists in it. And when I was talking to one of the engineers who worked on it, he said one of the things that was so great for them is that it got them a design that met the weight and volume requirements for the space shuttle. For the space shuttle, and met the specs that they needed to for the actual antenna performance that it needed. And it was a design unlike anything they'd thought of before. And it kind of made the engineers break out of sort of whatever their conventional thinking had been. And this engineer I spoke to said it really freed them up to be able to be even that much more creative and inventive. Okay, so let me talk about different modeling approaches you might use. So we have one approach that we call the solver-based approach. And this works at the moment for all optimization solvers, both in MATLAB Optimization Toolbox and the Global Optimization Toolbox. I'm going to get to the global optimization techniques in basically the second half of the talk. And basically what you do is you use MATLAB numeric arrays, matrices, vectors, and functions. And we have programmatic ways to put in the equations. So we know what we want to minimize, and we have to specify what the relationships are between the inputs and outputs, and whether there's inequality or equality relationships, constraints that are holding information in them, and upper bounds that we expect our solutions to lie between, like -10 and 10 or something like that. And what we'll do is return the value, the function value, and the location x, remember that'll be a vector x, of my unknowns. And you can see that if you don't want to specify everything, you need to know what order things are in so that you can put in all of these extra optional arguments there, placeholders for them. So you can do that, and we've been doing that for many years. And then we switched Well, we didn't switch. We added a problem-based solver. And this at the moment is just for optimization toolbox solvers, but it will be migrating eventually to the global optimization techniques as well. And in this, what you use is use optimization variables. You can think of them as sort of symbolic variables, but I can put the constraints on them. Like I can say, here's my X variable, my optimization variable, and it happens to have lower and upper bounds. And then my objective function here. And then I can put in constraints and I get to name them. My reward has to be bigger than or equal to this relationship with the inputs compared to a target. And then all I have to do is say, I want to get my solution out, at the location of it, and the function values, and I just call solve. And solve with the P, with my problem, has enough information to know what kind of problem solver you need to solve it, given the constraints that are in there. Okay, so that's all very hypothetical, but how does it really work? Well, I'm going to show you next, but I'm going to do a really simple problem at first, one that you probably know how to solve in MATLAB already. And if not, then you get to learn. Okay, so suppose I'm given some data, and you can see I have the data values here. And I'm also told they come from a process where my output is equal to, my response is equal to C1, a constant we don't know yet, plus C2, another constant we don't know, times e to the minus t, an exponential decay with a coefficient of -1. So we're not free to change what the exponential constant is here. That's given for whatever reasons. And what I like to do is I always like to plot the data just to make sure they make sense. If I don't do that, it turns out I frequently will be fooled because I might have mistyped one of the numbers in or something like that. So how do I think about this in MATLAB? Well, let me show you. I think about it as a linear system of equations. So we were told that our response is equal to C1 plus C2 e to the minus t. I'm a MATLAB person, so I'm going to convert this into system of linear algebra equations. And I'm going to have a matrix that is a matrix of ones to multiply my C1, and a column of e to the minus t to multiply my C2. And I'm going to call this first matrix E, and then my unknowns are the C1, C2. And so if I put the numbers in from the previous page, you see, well, C1 is just times 1. So that's just 1 here. This is my E matrix. E to the minus 0, of course, is 1. E to the minus 0.3 is whatever it is, and so on here. And what we want to do is we want to solve this system of equations, which is 6 equations and 2 unknowns. And we'd like to solve it exactly. Now you probably know where I'm headed, because if you've done anything like this and you have more data than the number of unknowns, it's pretty unlikely that you're going to be able to solve it directly, because when we collect data, it's not perfect, okay? And it's not necessarily because you're doing something wrong when you're collecting the data. That's just the nature of data collection. There's issues that come up with things, whether it's because, you know, the electricity isn't always exactly 100% 60 hertz or whatever. So instead of trying to solve this exactly, we're going to solve E times C. So this is going to be the C's that we want, our optimal ones, minus the response that we've measured. And we're going to try to minimize the 2 norm of this. And now you can see that this least squares problem becomes an optimization problem. So least squares is an optimization problem. So let me come over to MATLAB and let's see how this works. So here you can see I have the data that I have in the slide, and I'm going to just run this from my script. I'm going to actually, at the moment, minimize the tool strip so that you can see more at once in my window here. And I use run in advance so often here, run a section in advance, that you can see I've already added it to my quick access toolbar right here. And so I can just run that section in advance. And now I can make a plot. And in case you haven't ever seen a live script before, which is what I'm running, you will see that the output comes right directly into this window. You'll also notice, for those of you who are not familiar with live scripts, that this isn't a plain MATLAB code file, although it is a MATLAB code file. It's a live script. It's being run from the live editor, and it has a different extension instead of .m.mlx. And there's a whole bunch of tools on the live editor tool strip and accessories that you can use to help you maneuver with these. But I'm not going to spend a lot of time on that. You should be aware of it. So here's my plot. This is one of the nice things about the LiveScript too, by the way, is that you get a collection of everything all in one document rather than having a figure window open here and something else open over there and so on. It collects all the artifacts for you so that when you're all done, if you wish, you could save it into, let's say, a Word document so someone else could see what you did with your experiments. Okay, so we could add a title to this. And when I do, you can see we add the title. One of the things I didn't point out here, let me come back here, is you'll see when I put my mouse over here that there's some activity I can do. So for example, I can zoom in. I'm not going to bother to zoom in right now, but know that I can interact right directly with the graph in here, which is really nice. And I'll do that for real in a moment. So we added a nice title here. And this is the problem that I had on the slide. We're setting up our matrix, our E matrix, to be ones, the first column, and X e to the minus t, and here you should see it for our 6 values. E to the minus 0, which was our first point, t equals 0, is 1, so that makes sense. Now, here's the headache that starts. Okay, MATLAB, for better and worse, actually really for better, has a lot of choices. So how do we choose what to solve? Well, I'm a real believer in the documentation helping me, and so I've actually opened the documentation already. And we can come over here and I can look at the optimization toolbox and we can see a whole bunch of different topics here. You know, we could see how do we go about doing this. And I can look at the getting started and some different things, the toolbox solvers, let's say. Okay, here's a description of the solvers. Well, if I look at the description of solvers, that may help me, but I actually already know 2 other places in this documentation that are going to help us. One is problems handled by optimization toolbox functions. And you can see we have a collection of them: minimization functions and multi-objective optimization problems, equation solving problems, and least squares type problems. And there's also a decision table helping me decide which kind of problem to use. But I'm going to come to the least squares section here, and I'm going to spend a little time, and I'm going to make this bigger so that you can read it more easily here. And I'm going to move this to the side so that we can get as much space as possible. So you can see linear least squares. Minimize c times x minus d squared. That was like our e times c minus, what did I call it? E times c minus, it's in my slide here, e times c minus y. Okay, let me come back to the here. And there's a 1/2 simply because a lot of these optimization problems grew out of trying to find minimum energy. And if you have F equals ma and you integrate that, you basically get 1/2 mg squared or something like that. And so there's the half there, but the half or not doesn't matter. So it says when you do this, you use ML divide. How many of you have ever heard of ML divide? Maybe not so many. It's like, uh-oh, what's going on? Well, let's click on this, and I'm going to click on it and open it in a new tab. And when I do, you will see ML divide. It's also our friend backslash. Okay. And so normally you're going to solve your least squares problems this way, which is the way we try to tell you is the best way to do it. And there's a lot more information on here. In fact, if I bring this back now, what you'll see is there's information on this page, talks about description. It has examples, which are great, especially if you have something particular in mind. Maybe there's one that will have what you need. And then it will also have algorithms. It will have see also. See also is really helpful. It'll tell you first when it got introduced. It'll give you a bunch of topics where we have more discussion, and it will tell you the names of a whole bunch of different related functions that may be useful to you. So let me come back here for a moment. That's ML divide. What else can we solve? That's with M equations and N variables, and we say nothing about the relationship between M and N. We don't say that M is littler, M is bigger, or whatever. Another one I can solve looks like the same problem, except now there's constraints. We have a constraint that the x's are non-negative, also known as non-negative linear least squares, LSQ non-neg. Or we could have a constrained linear least squares, and we could have inequality constraints on our unknowns, our C's in my example, X's here. We could have equality constraints, and we could have upper and lower bounds. And then I have some nonlinear possibilities when my function isn't linear like this. And so I'm going to just give it the function. And so that's nonlinear. And we can have this first one with upper and lower bounds. And we can also do curve fitting where we nonlinearly fit a curve to data. And again, we can supply bounds. So let's come back to our MATLAB code here. I'm going to set up, as I said, my matrix, and we figured out we want to use backslash. So I'm going to come here and I'm going to use backslash, and we got some numbers here. Okay. Now, I don't know about you, but I am very much a verify person. So I want to like see, does this make sense? And so what I'm going to do is I'm going to make a curve from these values, the fit values, and check to see what they look like compared to the actual data we have. I'm going to click there. And now you see I've got this red curve, and we can see this point is below and that one's above, and we'd have to zoom in. Well, I can zoom in. So let's just come here. Let's see, is this one above or below? It happens to be above too. Notice how MATLAB will offer when I zoom in to update the code if I want, so that I'm always zoomed in. I'm not going to do that this time, but it's really nice that you get to do this interaction. And if you like the results, you can just commit that to the code right in the beginning. Well, there was nothing that I set up in the problem that said anything like point number 1 or point number 4 has to fit through my curve exactly. And so let's just look towards the beginning here, what happens. And you can see my first point is actually above the curve that we fit. No problem. In fact, we have some of these points above and some below, and we expect that because if all the points were above or they were all below, we could shift the curve up or down and get a better fit to the data. So we expect there to be some above and some below. All right. But maybe I actually know something else. Maybe I have a constraint on something. For example, if I'm working in a lab, I may very well control the conditions at time t equals 0 really, really precisely. And so I might, excuse me, I might want to add a constraint that tells me that I want to fit my curve exactly through this first point. Whoops, sorry about that. I have to get my mouse out of there because I know this point is correct, okay? And so what I need to do is I want to do the same kind of problem we just did, but I want to add in a constraint. And my constraint is that if we think about the equation, E1 times C1 plus E of 2 times C of 2, I want that to equal 0.82 in this case to my Y of 1. And so I can put in that constraint here that the value is going to be at, because my first C value, we know that C1 is our first coefficient in the E matrix is 1. The second coefficient in the first line of the matrix is e to the minus 0, which is 1. So I happen to know that the first input C1 and the second one C2, I want them to equal 0.82. And the way I would do it in the solver-based way is with this, and I remember I have to be careful about placing all the inputs in the right list in the right order. And here you can see, here's my 1 times 1 equals Y of 1. But I can do it differently. I can create an optimization problem now using the problem-based methodology. And I'm going to say I'm an optimization variable X and it has length 2. And I want to minimize it. And here I'm giving it the objective. And my constraint is that the intercept is that x1 plus x2 equals 0.82. And now I say solve it, and let's see what happens. And when you do, you'll see that it tells us that it shows LSQ lin, which is the thing that we saw in that table before. And now what I can do is I can compare my solutions. Now, if you look up here, you can begin to see that there's a yellow line and a red line, but The solutions are pretty tightly the same along in here. They're not massively different. Let me turn that on, just in case it wasn't. Okay, and I'm zooming in, and now you can begin to see there's some separation. And if I want to, I can start panning over. And I'm just going to zoom out because what I want to do is I want to zoom in here. And now towards the beginning, you will see my first curve, again, didn't fit through the original point, but my second one does. Because now I've added the constraint for the solution. So it's not the optimal solution, but it is the optimal solution given that we have that constraint that we want to impose here. Okay, so that in a nutshell is these squares and how you go about solving things in MATLAB, both from a solver point of view and from a problem-based point of view. And if you have any questions, I'm sure you're being well taken care of by my colleagues on the chat, but feel free to put questions in that chat so that we can answer questions as we go. Okay, the next topic I want to talk about is nonlinear optimization. It turns out that almost all of the interesting problems in the science and engineering worlds and finance worlds, they're not linear, which is too bad because linear are pretty relatively easier to solve. But the real world doesn't work that way. So we want to figure out ways to deal with nonlinear problems and get to good solutions. So I'm going to show you one example here. And here you can see I have a highly nonlinear function. We're taking the log of something that depends on x squareds and x's and x to the sixes. You can see the x cubed and the x and all that, mixing everything up here. And here's the shape of the surface here. And we're going to only look for solutions between minus 2.5 and 2.5 in both x and y. And we can guess that somewhere down in here, we don't know exactly where, there's a minimum. So what I want to do is I'm going to come over here and look at that. Okay, so I'm taking advantage of one of the features of the tool strip here to add a favorite. And one of my favorites right here is clear, which clears my workspace, home, which clears my command window in case, but doesn't clear the history of it, and close all closes any open figure windows, which I shouldn't have any open since I'm working with live scripts at the moment. But I'm going to hit that, and now you'll see my workspace is empty so that we're starting from something new. And now I want to take the equation from the slide here, and I want to put that into MATLAB. Notice I was able to put this in using the LaTeX equation editor here. Okay, so these live scripts are really great for conveying technical information to other people. Now, instead of creating a function file for the function, I'm going to create what's called an anonymous function. This is a function in this case that depends on two variables, x and y. I could have made it one variable that it was of length 2, x1 and x2, but it's clearer to get the correspondence between these two if I write it this way. And so here's my objective function, and I'd like to plot my objective function. And so because I kind of like verifying that I did the right thing. And here you'll see that we have the plot. Now, what I'd like to do is try rotating this so that we can kind of see into there. And maybe I really like this view better, so I can update the code there. And now you'll see that if I run this again, it runs the code that's there, which now includes the code that I added. Okay. And now I want to create an optimization problem. So I'm going to just create a blank problem here, and I'm going to define the variables. We're going to define both x and y, and as I mentioned before, we're going to constrain them to lie between minus 2.5 and 2.5. And I'm going to define the objective function here. And remember, I was just doing this in LaTeX before, and I was doing this as an anonymous function wherever I did it here so that I could plot it. But now that I'm going to actually use it in a problem, I actually have to put it in as the objective function, and I put in the same, basically the same code, if you will, for the objective function, but it needs to go in my problem since I'm doing a problem-based formulation here. And now what I'm going to do is I'm going to set an initial point to start at x equals -1, y equals 2. And I'm set optim options. Whoops, I am in the wrong folder. Now you know what happens if you're not in the right place. I didn't mean to do that, but there you go. Okay, and I'm setting some options. I wanted to plot the update, and as it's going, it was plotting, and it said we started here. That was my -1, 2, and then went here, and and so on. And it tells me more information. It did it in 25 function evaluations, which isn't bad. Now, it used to take a lot longer, but there's something new that's in this. This is the release in which we introduced automatic differentiation into the optimization toolbox. And the solve function by default will use automatic differentiation to compute the gradients. Now, remember when I was talking heuristically earlier, I said we estimated the gradients. Well, instead of estimating them, it's taking the code that it has and it's evaluating the gradient at that location correctly using this automatic differentiation. And we have a lot of documentation telling you more about that if you want. Because if I don't do that, what I have to do for each point is I actually, for each dimension, as I need to measure it a point ahead and a point behind and the other dimension, another dimension. So if I have a lot of dimensions, I have to evaluate many nearby points so that I can estimate what the gradient is and then find the right direction. So in this case, we find the right direction through automatic differentiation. And now what I do is I come and I can solve the problem. In this case, I'm going to solve it. Let me see if I can show you. In this case, I'm going to do it doing finite differences, which was the old way it did it by default. And when I do this, what you see here is we get pretty much the same solution, only instead of 25 function evaluations, it took 69. It took a lot of different steps, partly because each evaluation where it was estimating the gradient wasn't as accurate as the actual gradient. And so it had to make up for the fact that it wasn't taking the best possible path, but a guess, an estimate of the best path. Okay, well, when you're working with problem-based workflows, there are sometimes optimization problems that you want to express that can't be expressed directly as an optimization expression because there's an unsupported function. And so we have a way, I'm not going to talk about that in any detail, but that's a way, there's ways that you can deal with that. And then I can solve my problem in a problem-based way. And when I use this, what you can see is I can edit. We already had one from long ago. I'm going to open the edited objective function, and you can see that it has input variables that will return the objective and the gradient. And then you can go through and see how it's doing that, and it will show you what it did. Here's the generated function, and it calls a different function for the objective. It already knows generated function 1 is going to be derivative there. Okay, so that's all well and good, but that's a little bit of overhead thinking about a lot of that stuff. Now, suppose I want to do this. I want to show you another way that you can do this that might make your lives even easier. And you'll notice up in the live editor now, there's a bunch of things, I can format the text and I can run code and we could insert links and equations and things like that, but I can also insert tasks. And if I look at the tasks, we have a bunch of tasks for data pre-processing and working with timetables and tables in MATLAB, and we have an optimization one. So what I'm going to do here is I'm going to set things up to work with that optimization task. And in this case, it doesn't work with structures, so I'm going to get the data variables, the lower and upper bounds, out of my solver problem, and I'm going to set my initial point, the starting point. And now I'm going to bring in the optimization task, and here it is. And if I want to, I can minimize this at first, and this is really a crazy looking piece of code. I have my solution that I'm going to get and the objective value, and we're minimizing the objective function using the fmin_con solver. Okay, well, what does it look like in here? I specify my problem and say it's nonlinear. I'm going to give it lower bounds and upper bounds, and you can see all of this here. and then we choose a solver, and I could go and try different solvers. And then I can say my objective function, where is it? And in this case, it's in the file edited objective function. We're going to give it an initial point of x naught that was in our workspace. We're going to get our lower and upper bounds from the workspace. We can specify all kinds of solver options if we want. In this case, we're going to have the objective return gradients as well. As you can see, so there's a bunch of things there. And then I get to choose what to plot. And let me run this. Okay, and when we run this, you can see that we ended up with basically the same thing that we ended up with the problem-based version. But if you want to see what the code is, I can actually come and look at the code. And I'll tell you that I looked at the code for all of these tasks very often early on. Because I don't like black boxes and I didn't kind of trust what was going on. I've now looked at enough of it that I don't really need to look at it anymore. And the nice thing about this is it allows me a chance to come here and play around with a bunch of things. Like I could play around with different starting points, for example. I might have a whole suite of initial points that we wanted to try. So we could try a bunch of things there. And once I settle on what I want, I can come here if I want, and I can convert this to editable text code, and then I can forevermore run from the text code if I want. Okay, so there's that. Now, when we did that, interestingly, we started and it didn't go on the regular path. It did something else a little bit funny, but that's okay. And we got the right answer again. Now, if I'm thinking about supplying the gradients, because that's one option I can do. I can supply them myself, gradients and Hessians if I want. I can easily do that for 2 dimensions, maybe even 3 dimensions. But if I have a problem that's 10-dimensional or 100-dimensional or 1,000-dimensional, I'm going to type something wrong at best, and I'm going to get the algebra wrong on my piece of paper. I'm going to make a sign error or something. I just know it's not going to go well. But I can actually harness the power of the symbolic math toolbox to help me with that. So I'm going to solve this problem one more time right now, and I'm going to create some variables, symbolic variables, xsim and ysim. You can see in the symbolic world, I'm now going to put a function, the same function we've had, and I'm going to let the symbolic toolbox compute the gradient and the Hessian for this. And I'm going to turn these symbolic functions into MATLAB functions here. And then what I'm going to do is I can use the optimized task once again to solve the problem this way. And when I do, it shouldn't be any surprise. We get the same answer we got before. So those are a whole bunch of ways. There's another way that I could do this, and I could add parallelization in and make things faster again, depending on what I'm willing and able to make parallel here. Okay, so we can do nonlinear optimization in MATLAB. We give you a bunch of different ways to do it, whether you're going to take advantage of automatic differentiation or not, whether or not you're going to take advantage of tasks in the live editor or not. And of course, you can just write your straight code if you'd like. Okay. There's another example that you will get in the downloads if you choose to download the code examples from this talk. And there's a little bit of discussion about automatic differentiation. Automatic differentiation is not the same thing as the symbolic derivative, because it does it at the local point at the time where it is. So that way, if you have like an if and else if, it's in the if, it's going to ignore the else part because it's in the if part, and it's going to work on the tree. And there's a lot more information in the documentation if you wanted to know more about that. And now I want to move to another kind of problem, which is a mixed integer programming problem. And these come up in science and engineering and finance regularly. And the idea is that we have maybe part of what we're trying to optimize is one of the quantities, one or more of the quantities might have to be constrained to be an integer quantity, like maybe 1 car or 2 cars. Having 1.3 doesn't really make sense in that case. So it also could be things like a binary decision, yes or no, buy or don't buy, and so on. And so I'm going to solve an optimization problem enforcing that certain variables be integer, and that's the way you do that is with a mixed integer linear program. So if I have both continuous And integer variables, here you can see a continuous one on the left and integer one on the right. And I have a linear objective function here and some constraints. I'd like to be able to solve that, and I do that with, as I said, a mixed integer linear program. One example that we have that I will not do is optimizing gift card spending. I'm going to do a different one, which is the traveling salesperson problem. So how do you find a shortest path through a series of points? Well, before the coronavirus came out, I used to travel around the world a lot, and I would make it onto basically most years 6 continents. I have not been to Antarctica, and we don't have an office there, although we do have MATLAB users there. But if I wanted to figure out how to travel around the world to all the MATLAB offices, MathWorks offices in a year, I might try something like this. So if we think about all the offices, and we have more than 5, but if I think of all the offices, what I would do is I would figure out all the connections in pairs between all the offices. And then one of my trips around the world would be a sequence of choosing some of the segments to go on, which are denoted by the green ones. And the red dash zeros are the legs that I'm not going to go on. And I could exhaustively go through this list for all of the possible permutations and find the best solution. Well, as you can imagine, doing that through permutations might not be the best way to go. So I'm going to clear out my workspace here, and I'm going to get in the right folder right away here. And I'm going to show you what to do. Now, one thing I haven't told you yet is my background. So you're gonna see my background come up just a little bit in this example, because I got my degree in geophysics a long time ago. And so I've worked on whole Earth problems where we had to think about the Earth as not even just a sphere, but an ellipsoid. So I'm going to take advantage of that when I can, just because I can. So MathWorks offices, you can see plotted here. We have more than 30. Oh, I didn't want to do that. It's okay. Maybe it's okay. And this is where the offices are. Okay. I don't want you to see that again more. No, you can't see more. My mistake for doing that. I will still go through the different. It's going to just keep doing what it wants here. Okay, so the first thing I did is I loaded the offices, and what you saw is that they came up in that web map. And I'll talk to you a little bit about the web maps, but a web map is an interactive map that you can run. It's in basically a web browser, and I get to put all kinds of different relief terrains over it. So I can put in, for example, world imagery instead. And if I want to, we could put in, because we have access to it, the U.S. Weather Next Rad radar, and we can see what's happening in terms of the weather in the U.S. at the moment. I'm going to put this back on the ocean base map, and you can see there's a few storms in North America at the moment. Okay, so this is a nice web map, and we can zoom in, and we can look at pan, and we can look at different places. I'm going to close this for the moment, and whoops. I'm going to come back here and run that section. And this is, again, where our different offices are. And you can see we have a bunch in North America. Let me make this a little bit bigger. A bunch in North America, a whole bunch in Europe, and of course, a bunch in Asia. And we happen to have one in Australia. Asia, of course, includes a bunch in India, China, Japan, South Korea. Okay, so what I want to do is figure out how many possible paths there are. Well, there's a lot. So what I have, you can see 2 times 10 to the 35 paths here. And let me clear the output again. So let's just run this again. Okay, so that's a lot of stuff. So even if I'm going to run in parallel on some big cluster up in the cloud or something, that's a lot of paths to consider, and it's kind of prohibitive, and it's not really the right way to try to solve this. Okay, hold on one second. So there was a question about the nonlinear optimization and does it work with non-convex functions? Non-convex functions, absolutely. The optimization works, but you're not guaranteed to get the global minimum. And that's when we end up going over to global optimization techniques, which I'll get to in the second half. The ones that I've just showed you so far have been not necessarily, it's not required that they be convex, but they're not going to be guaranteed to get you the absolute minimum if they aren't convex. Okay, problem formulation. Well, first I want to do is take all the pairs of points from all the different office pairs and compute the distance between each of those sets of pairs. Okay, and I'm going to do that. Here's where my geophysics comes in. Instead of doing it on a sphere, I'm going to do it on the reference ellipsoid, and I'm going to find the difference between office number 1 and office number 2, office number 1 and office number 3, and 2 and 3, and so on, all that sort of stuff. And now what, excuse me, hold on one sec. Okay, and now what I'm going to do is I'm going to create an optimization problem. This is for the problem-based solver. And I'm going to say what I want to do is I want to have my trips variable, and it's going to be integer, and it's going to have a lower bound of 0 and an upper bound of 1. And the trips is going to be number of trips by 1. So this is however many offices we have. Where's n trips here? It'd be n trips is 528. That was the number of pairs between all the different points in 33 offices or something like that. So what I want to do is I want to take those distances times the trips, whether the trip is on that particular segment is true or false. And I want to get the total distance I've traveled. And of course, what I want to do is set that to my objective, because that's what I'd like to minimize. So let's set up our problem. Let's add our objective function. And now at the moment, I have one constraint. And think about it this way. If we think about a particular office, what has to be true about me going to that office? I have to go to it once, and I have to leave it once. And anything more than that is wrong, because I'm either going to be there, if it's an odd number of times, I'm going to go in and I'm going to effectively go back there and stay there forever at some point. And if it's more than one, more than two, I'm coming back to it, and yet I've already been there. So what I want to do is I want to basically say, I want for all of the different possibilities, I want the number of trips at each one of the possible nodes between all of these different offices. I want them to be 2. I want them to have something coming in and something going out. And so that's the constraint on my trips, 2 trips per office. And now I'm ready to solve the problem. And so we're going to actually tell it we want to use intlin prog in the options. And you'll see we're going to get a bunch of outputs here. And let's just go. And when I do, what I'd like to do is I'd like to take our plot here and visualize our solution. And now you see a problem. Let me zoom in or zoom out a little bit. Let me come and show you. Here we have Dallas, LA, and San Francisco as one loop. And we have basically near Detroit and Boston, one loop. And then we have a loop in the UK and Ireland. And then we have a loop up here in Northern, and so on. And so we haven't gone around the world once, right? So we actually are missing some constraints that would help us, because each one of these only has 2 stops in it. But now I don't want more than one loop going around. Okay, so let me think about what that means. So what I need to do is I need to think about these subtours, and I want to eliminate each subtour somehow. So if we think about any subtour, let me go in here. If we think about this one, there are 4 stops in there. If I don't want that to be a loop, unless it's all 33 or however many offices we have, then in any given smaller loop, there's another constraint, and that is that the number of segments associated with these has to be at least 1 less than the number of actual stops, because I can't have it close on itself. So that's what I'm going to add next. I'm going to say I basically want to change the constraints so that I remove the possibility of a tour being there. And when I do that, I might get new tours coming up. But so what I'm going to do is I had 8 subtours to start, and I'm going to say, well, the number of subtours is greater than 1. Keep repeating these things. We're going to add some constraints, and we're going to say what's going on. We're going to see how many times we tried this. And when we did, oh, I think we didn't print it out. That's too bad. I think we should have printed it out. Maybe I didn't run that yet. I didn't run it yet. Okay. Now you'll see we end up with something. Pick wherever you want to start. And if I come here through Europe now, you'll see we don't have a loop within Europe anymore. We go up through Ireland, through the UK, down through Western Europe, up through Northern Europe. We come over to India, and so on. And so we get go from Japan down to Australia, back to the east coast of the US. Oh, I guess I made it so that it didn't go around. East coast of the US, and then we go across the US. So when I do that, we found that we had 8 subtours, then 5, then 2, 2, 4, 1. Now, I can't prove to you right now, but it is provable that even though I'm doing this in an iterative way, that I get to the optimal solution. And if you want to know more, I wrote a blog article on this last year or the year before. And then Cleve, who's our chief scientist and one of our founders, posted, and he said he didn't believe that it was an optimal solution. And then Mary, who also works at MathWorks and who's an optimization guru, said, yes, it is. And she showed him how a little bit on the blog and referenced some papers. So it is an optimal solution, even though you didn't solve it in the sort of direct way. We did this iteratively. And we ended up with a good outcome. And so then we can see what the output is, and we can see some different information. It says it found an optimal solution. There we go. Okay. Let me come back here. So now would be a really good time to ask your questions on traditional optimization, because I'm going to be moving on to global optimization in this next section, although I will still be referencing information about traditional optimization there, because some of the global techniques underneath use some of these what are called local techniques. So if you've got any questions, now's a good time. And I'm going to move on to global optimization. Let me actually clear things up a little bit. Let me close that. Let's take this one and get rid of it. Let me close that. Go here. Now I'm ready. Okay. So there's a problem with solving some optimization problems. So suppose we have this function. You can see it's the same function in all of these different plots. And all we're going to do is start at different starting points here. And we're going to use fmin_con, which is one of those local solvers, function minimization with constraints. And that the constraint is that we want the it to fit this curve, whatever a point on this curve. And if we start at point 0, you'll see we get a solution at 0. If we start at 1, we get a solution near 1. If we start at 3, the green is the solution, we get a solution at 10. So you'll see in only one case, when we start at 8, do we actually find what we can see by eyeball is the minimum solution. So what's going on in here? I think you probably have an idea, but let me belabor this point. And let's go here. Why didn't fmin_unc find the best engine efficiency solution here, which would have been up in here? And it's the same reason why we didn't in the first one. If we'd moved our starting guess, we might have found it. Now here's a third one. Why didn't we find a nonlinear regression that fit these data very well? These are pharmacokinetic data, and there's 3 decaying exponentials here with 3 different decay rates and decay and then constants with them. And you'll see that while we kind of mimic some of the exponential drop off over here, we in no way represent the data really well in the beginning. And the problem is that these problems don't have a single, they're not convex, and they don't have a single minima. And what we really want is we would like something like a global minimum here. And I'm going to show you some ways that we have a better chance of achieving that now. Okay, so our goal with global optimization is to find either the lowest or largest value of some nonlinear function that may or may not have many local minima and maxima. And here you can see a particularly pernicious one. This is called Rastrikin's function. Russian mathematician dreamt this up. And you can see it's labeled here that there's a global minimum at 0, 0, but there's a local minimum at every intersection of integers. So 0, 1, 1, 0, 1, 1, and so on. So it's pretty easy to fool this function if you don't start at the right place. And so the problem is that traditional solvers often will return one of the local minima, which is what's happening in my other examples there too, and not the global one. And so we would like to have some strategy with our solving that locates globally optimal solutions. Now, these are not guaranteed, but they have strategies which I will show you in the next few examples. They have strategies, they employ strategies that try to cover enough space, parameter space, so that you feel like it's been well represented, and if you have an answer, it's more likely to be the global one. Okay, so what do we have today? I'm going to cover a bunch of solvers today: multi-start and global search, pattern search, genetic algorithms, surrogate optimization, particle swarm, and simulated annealing. Now, I'm actually going to not cover simulated annealing today. It's in the slides, it's in the examples, but it never comes out to be the top one you want to do. Okay, and so I'm going to spend time on the ones where there's much more success and much more interest in general. And I'm going to tell you how they each work, and then I'm going to do an example, at least one example in each of them. And for many of you, I'm guessing that you've heard of some of these before, maybe even used some of them. Some of you may be experts at these and use them all. And some of you may not know what any of them are. And my goal now is to explain what they are at a high enough level that you have an idea what they each do, that you'll know what they each are by the end of the seminar. So let me show you the multi-start demo before I actually go too far here. And what I want to do is I'm going to come over now. I have a traditional MATLAB code file. And what I'm going to do is I'm going to run and advance a section here. And here we have that pharmacokinetic data, and you can see it plotted here. And now I'm going to put the label on it. Should have put the label on it. No, it didn't put the label on it. It just, that's for the when you publish it. And now what I'm going to do is I'm going to solve it. You know what I'm going to do? I'm going to make this narrower for right now. Hold on. And bring this over so that you can see what's going on. Okay, now let me run the example code right now. We're going to run LSQ curve fit. And when we do, you see that I had to give it, because it's nonlinear, I had to give it some starting values. I said all the B's were B1 through 3. The initial constants are 1, and the B4, B5, and B6, the decay constants, are all 0.25. And lo and behold, when we do that, we get a mean squared error of 2 times basically 0.2. So it's a pretty high mean squared value. And when we finish, we get the B1, B2, B3 being some values near each other. And more importantly, the B4, B5, and B6 basically being one decay constant. And that, if you think about it, is because we started with all of them nearly the same. But the point of multi-start is actually to start at a whole bunch of different locations that will map through your parameter space more evenly. And you can see in this case, I'm going to let it choose the points, but I'm going to say run 50 of them and get me the answer. And so I could either supply the points, or I could say, do your best at distributing them evenly. And when we do, you can see I'm running through a whole bunch of different problems here, and the mean squared error is going up and down, depending on what we find. And this is the very last one. It doesn't mean it's the best one, but it's the last one that came out. And our starting values were listed here for minus 0.6 and minus 5.2, and decay constants that were not all the same. And when we get done, you see we have a mean squared error of 9 times 10 to the 3. So a factor of 1,000 or so, or 150 or whatever better. I'm not sure. I don't remember. But yeah, 500 better, I think. And we have two different decay constants, it looks like in this case. But because it was the last one doesn't mean it's the best one. And one of the nice things about multi-start, which said start it and run it 50 times, and I showed it to you there, is that it will return me the solutions in order of best to worst. And so I can get the best one here. And when I get the best one, you can see it's even better than the last one was. One mean squared error of 1.4 times 10 to the minus 5. And you can see now I started at 3 very different decay constants, and I ended up at 3 very different decay constants, not 2. And now we represent the data fairly well. If I wanted to, because of those 50 problems being 50 different start points, I could run them in parallel. I'm not going to do that right now, but you would get a speed up potentially for that. Depends how many cores you have and how much you're speeding it up with your parallel pool. So you can see by not forcing me to make up some start point that I don't really know a good value for, multi-start can help me do better than we did before. Okay, so I'm going to put this back, and I'm going to clear everything out. Okay, now I want to describe multi-start a little bit. A multi-start is one where we're going to run a local solver underneath that other one that you just saw. I was running fmin_con. For each set of the start points, remember I had 50 there, and there's an option to filter starting points based on some kinds of feasibility. And because we can do it from each starting point separately, they're not dependent on one another, I can use some parallel computing. And so let me come over here. Let's change and let me run this. And instead of running the code directly, what you're going to see now is that I'm going to run this little demo app instead. And I'm going to select a problem to run. We're going to use our function peaks. The function peaks has a smallest value down here. It's got its next smallest value here. It's basically got these the 3 peaks, but then the 3 valleys, and we're going to go for the steepest negative here, the deepest negative over here. Okay, and so I'm going to select a solver, and when I do, I'm going to select multi-start. And if you wish to, you can change the number of starting points. I'm not going to do that right now, and I'm just going to run it. And so we can see starting point number 1, and it starts over there, and it's basically crawling into the corner. Okay, and pretty soon it's going to start point number 2, and you see it gets to what we happen to know is a global solution pretty quickly, but it doesn't know that yet because it has to continue sampling the space. So it gets to another local minimum here, and then we go from here somehow and get into there again. We're going to dive into the corner again, I'm betting. And now you'll see this is not the actual optimization speed. This is our drawing speed because these optimizations are pretty fast. So I'm going to make it go a little faster so that you don't have to watch it just draw slowly. Again, that wasn't MATLAB drawing slowly or the optimization going slowly. We slowed it down so that you could watch what was going on. And I will probably slow it back down again at some point. And when it gets all done, it rank orders all the different points it found, and it finds that this one is the global one. Okay, let me just have that hang out there for a minute. And now I want to talk about global search. Global search is a multi-start kind of algorithm as well. It's going to also call fmin_con from multiple start points to try to find a global minimum. By the way, because both of these are using fmin_con underneath, the functions that you're minimizing need to be smooth and differentiable because they're using gradient-based methods. So they can't have big jumps in them or anything. And in this case, it's going to filter or remove non-promising start points. So how does this work? So what we're going to do is, again, this is the blue is our deepest well, and then the red one, and then the green one. And so we're looking from on top. And what I'm going to do is I'm going to pick a starting point, and I'm going to to do a local search there with fmin_con, and we find a local minimum. And then what I'm going to do is I'm going to draw a radius, a circle of that radius around that point. Okay, and then I pick up a whole bunch of different points, and we can look at the different points, and we find that there's one that's a minimum point there, -2. And so I'm going to come here, and I'm going to run the optimization from there. And when I do, we get another local minimum, and I'm going to draw a circle of that radius around that minimum. And now we get a bunch more points. And there's a couple things to note about this. The first is that there's points inside those circles. Now I'm going to call those radii of convergence, but they're not formally. We didn't prove any theorem that says that's true. But from a pragmatic point of view, it ends up being a useful concept here. So since it's inside that circle, I'm going to suggest that we probably already know the answer, and we don't need to spend time working with that point, but rather with points that are points that will let us explore the space more fully. So we get another point here. Its current penalty value is 6. But our current penalty threshold value that we got from going over here was a 4. And so I really don't want to start with a higher one than I already have. I already have something better. And we look around and we find another start point. Its value is -3. And so what I do is I run a local optimization, draw the circle around it, and then we look for another point. And what happens is it happens to find the same location I just showed you. We draw a circle around it. We can remove the inner circle because it's completely contained in the outer circle. That's one thing. And the other thing you'll notice is that there's overlap between these basins. That can happen. We don't know for sure in that case which point, if it's in that overlap, which one it will converge to. But we think we have an idea where it's going. It's going to go to one of the points that we know, we think. Okay, and so that's the idea behind global search. So let me come over here. I'm going to go like that. That's going to be easier. And we're going to pick global search now. And I'm going to back off on the speed just a little bit. So we do our first point, and it crawls in the corner. And then it's going to start looking for points to pepper around. And it finds a solution. In this case, it looks without doing 10 of them. And I didn't tell it to pick. What I did that I had other parameters that controlled how it was going to choose whether it converged or not. And there's information about that in the documentation. So that's global search. And remember, both of those require smooth differentiable functions. The next thing I want to talk about is pattern search, also called direct search. And this is an approach that uses a pattern search directions. Remember when I was doing that engine efficiency problem and I said I could take a step in one direction and keep going until it got worse, and then I'd back off partway, and we iterated along one dimension and then another dimension? This is going to sound a little bit like that, but it's really not. But it's going to use an approach that uses a pattern of search directions around existing points that we've already investigated. And around those points, we're going to either expand how far we're going to look, or if that doesn't work, we're going to contract the search. And because of always just evaluating the function and not gradients, this works on smooth and non-smooth functions. So let me show you how this works. Here's a point. I can evaluate the function at that point. We get 3. I lay down my grid. In this case, it's going to be a grid that I choose to have step size of 1. You can change that. And I'm going to apply my pattern vector, and I'm going to look for new values. Well, if I want to, I can say, I just want to stop when I get my first successful poll. 2.8 is less than 3, and I could stop right then. And that's the default. But what I'm going to do is do what's called a complete poll. So I'm going to look at all 4 points in this case. Remember, there's going to be 2 points for every dimension now. And what I'm going to do is pick the best one, which will be this one. And I'm going to take that point, and instead of just putting the pattern down, I'm going to expand. So here's the expansion. I already know the value of this point. And now I get these 3 points, and I evaluate them, and we find out in the complete poll that this point is best. and I put down a new expanded grid from there. And when I do, I get this point, and all the other points are outside my limits. So expansion isn't going to work. So what I do is I contract. And when I contract, well, I happen to know this point, but now I get 2 more points to look at, and I keep doing this expanding and contracting until I get to a minimum. And what you'll see here as we do this is, even though it doesn't look like it, we're actually sampling the space a little bit better than you may think. So I'm going to come over here to pattern search, and I'm going to use complete poll true because that's what I just showed you. And my expansion factor is going to be a factor of 2, and my contraction factor is going to be a factor of 2. You don't have to have it be that way, but that's what I'm going to do here. And now I'm going to solve it. And we pick a point, and you can see it's expanding and contracting and expanding and contracting. And it's going to sit there and infuriate me. So I'm going to speed this up. And it should get to this solution that way. Okay, it turns out that by doing this, it focuses in more and more in a fine-grained way in an area that's very rich for exploration, for finding the actual global value here. Okay. The next one I want to talk about is genetic algorithms. Well, what is a genetic algorithm? I'm sure you've all heard about them. Many of you have some idea what they are, or maybe you're even expert in it. And it uses concepts from evolutionary biology in terms of how to create the next generation of possible points to explore to see if they're optimal points. And what we do is we start with an initial generation of possible candidate solutions, and we test them against our objective function. And the ones that are closest to minima are good in some sense because they minimize the objective. They minimize the objective better than the other ones. And so that's what's going to be a driver for which ones we want to keep. And we're going to basically get successive generations from the first generation through selecting. So selecting some of those good values, taking them and doing crossover and mutation. Well, to explain crossover and all these concepts, I'm going to assume we have a binary case, basically trues and falses, but the idea is the same regardless. So selection says retain the best performing strings. In other words, those that were near some minima. So here we have a couple that we chose, and you can see these are parents and they have a bunch of 1s and 0s. They have some 1s and 0s in common, but they definitely have some that are different from one another. Crossover says take these two and create a child from that takes its genes from either parent 1 or parent 2, 1 by 1 by 1. And you can change the percentage, but on average, we say on average, a child should get 50% of its genes from one parent, 50% from the other. But that's the average. So you're going to have some get 30% and 70% or whatever. And if you don't want it to be 50-50 anyhow, you can change that. But that's how we get this bit string, if you will. And the final way is mutation. And mutation is we take a parent, and on average, we change a certain percentage of the genes, and those are the mutations. And again, not every child will be different from parent by exactly 30% or whatever we choose, but on average, they will be that. So let's come here and look at genetic algorithms. So we evaluate the initial population, and we select a few good candidates. Notice that we've selected ones that are going to have those lowest target values because they're nearer to our minima. Okay, and we're going to generate a new population based on those. The yellow ones are the old ones. The gray ones are the old ones. We're going to generate a new population here, and we're going to evaluate that population, and we're going to choose a few good ones from those. And do again after this, we choose the few, and then we do crossover and mutation to generate the next generation. And all the gray ones are ones from previous generations. And what you see is if we do this long enough, we end up getting to what looks to be a good solution. So let's do GA here. And again, there's a bunch of options here. I'm going to leave them the way they are. And I'm going to start off here. And you can see they were distributed all around, but in this case, fairly quickly bunched up. And they're still going to spend some time duking it out in there. And in fact, I'm going to help it along so it finds a solution that way. Okay, And again, genetic algorithms, kind of like pattern search, does not require gradient calculations. So it, as well as pattern search, can use non-smooth as well as smooth functions. Don't need to be differentiable. Okay. And you can actually solve mixed integer optimization problems using genetic algorithms. And we'll see whether I get to that. I'm not sure I want to do that, but there's some good examples there. You'll get them. There's another relatively new solver in the optimization toolbox called surrogate optimization. And what surrogate optimization is really good for is an approach that creates and optimizes a stand-in, a surrogate for the actual function. This is useful in cases where your actual function is extremely expensive to evaluate. It might be solving, some very large system of coupled ODEs. And what it will try to do is, in a local area, represent them by some radial basis functions, which are really inexpensive to calculate. And it will do a local optimization, basically a localized optimization based on that function surrogate. And then it will check with the main function from time to time to see if it needs to be adjusted, if the surrogate needs to be updated to better reflect the behavior of the function, the real function at that time. So it searches randomly when it's doing that and to explore it, and then it adaptively refines where it's looking as we go. But it can do that with the radial basis most of the time and not the really expensive function. Again, since these are function evaluations and not gradients, it works on smooth and non-smooth problems. So here we go. We have some random points and we have an incumbent point. So this was our last good point. And what we do is we have some adaptive points. These adaptive points are based on the radial basis function points. And then what we do is we have a new incumbent point, which is over here, and we generate some more random points and we get some adaptive points, and we keep iterating until we get a solution. Okay, so I'm going to come over here and we're going to go to surrogate optimization. And again, there's parameters that you can choose. And I'm going to try to back off here. We'll see if I want to speed up again. And what's it doing? Maybe I'm doing something. Here we go. Here we go. It's taking it a while. Okay, so the dots are surrogate functions. The triangles are the touching base with the main function, going back to it. But it's spending a lot of time looking at all of these. It can explore a lot in surrogate land in a cheaper and faster way than it could with the main function. And then what it does is it finds a new start point after a while, just to make sure that it's not sitting over here just because it couldn't get out because of the radial basis function. Turns out that all roads end up leading it to here. And so when I go faster, you can see we reach a solution there. Okay. And you can do that same thermistor example that I didn't really talk about before through genetic algorithm or surrogate optimization, and you have the code for that in the download from the YouTube page there. So another choice we have is particle swarm optimization. And this entails having a collection of particles that are moving in a region. And what I like to think of is either a flock of birds flying or a school of fish swimming. And if you've ever had the chance to either look up in the sky and see a whole bunch of flock of birds going together, or snorkeling or diving and seeing, or looking in an aquarium and seeing a whole bunch of fish moving together, this is what the idea is happening here. Particles get their velocity by being affected by the points nearby, what their other velocities nearby are doing. And so it will update its position and its velocity based on itself and its surrounding areas. And while it's doing that for one particle, all the other particles nearby are doing the same thing, and they're all influencing each other. Again, we're going to evaluate function points rather than gradients. And so this again works on smooth and non-smooth functions. And so if we start off with vectors with a position and velocity here, what we can do is we can find the best location for the new particle based on its previous velocity, based on velocities from other neighboring particles, and we can do the vector addition and get a new velocity. And by the way, we do that for everything all at the same time, so they're influencing each other at the same time. And then they end up moving. Their criteria for how much they move is also influenced by the function, how well they're decreasing, how well the function is decreasing as they go. So let's come here and let's choose particle swarm. And I'm going to slow this down so you can really see it. You can see the swarm starts all over. So it's really sampling a fair amount of the space. And you're getting a collection bunching up. And you may or may not get one that goes rogue at some time. I'm going to let it just duke itself out in there for the moment. Okay, so we have a solution. So let's run that again because it should be from different random numbers. As what happens with a flock of birds or whatever, you might see all the birds but 1 or 1 and 2 peel away. So sometimes not everything will go towards that, but there might be 1 or 2 rogues. That's okay still, depending on how many you've started with. You still have found what the group ensemble basically thinks is the local minimum there. So that's particle swarm. I told you I was going to leave out simulated annealing, and I am, but you'll be able to look at it yourself in the slides if you want to, because I want to come and just talk about the overview of all this. So we have a bunch of solvers in the optimization toolbox that are gradient based. In other words, they're meant for smooth functions that have smooth objectives. In other words, they're differentiable and they may have constraints. And we have a whole bunch of different problems. So we looked up before when we were looking for linear least squares, we found some of that, LSQ lin and so on, but there's a whole bunch more here to help you that we didn't talk about all of them, but there's a bunch of different functionality here. So a bunch of different functions depending on what kinds of constraints you have. Global optimization toolbox solvers search for global solutions, and global search and multi-start are well suited for smooth objectives, remember, because underneath they use a local solver, in other words, one from optimization toolbox like fmin-con or fmin-unc. And so they rely on gradient operations, and they can return the location of local and global minima, like multi-start will return all the different minima it finds, but in a rank ordered list. The remaining 4 of these work on smooth and non-smooth problems. They are derivative free. You do not need a gradient. But what we have observed is that GA, simulated annealing with bounds, which you didn't see in action, and particle swarm generally require many more function evaluations in order to sample the search space really well. And typically, pattern search and surrogate opt require far fewer function evaluations than those. With the caveat that surrogate opt is basically most well suited when the real function you're trying to evaluate is kind of prohibitively expensive from evaluating, and then you supply it with a surrogate way to do that to approximate things. There's also some other global toolbox optimization toolbox solvers for multi-objective things when you're trying to get a balance between minimizing something and something else. There's 2 different trade-offs and you're trying to figure out what to do. And similarly with Pareto search. MATLAB also have some solvers, fmin search, fmin bound, univariate, zero finding D0, and LSQ non-neg, that non-negative least squares there. Okay, how can you speed things up if you're actually working on optimization? And global optimization can take advantage of parallel computing. And these are the functions that can do it. For each of these, this first group, they can evaluate, at each iteration, you're going to evaluate a whole bunch of different points. Those point evaluations can be done in parallel. For multi-start, the starting points can be evaluated in parallel. For optimization toolbox, if you're evaluating the gradient by finite differences, those function evaluations can be done in parallel. And you can always use par 4 or par F eval as well. The app that I've been using is really not even an app. It's really a demo. Okay. And so it's not where you would go to do your optimization. You're really going to use the functions themselves. With the optimization toolbox, you're going to either use the solver-based method or the problem-based technique. For the global solvers, at the moment, you're going to be using the solver-based technique, and you will have options in later versions of MATLAB at some point to begin using the problem-based methodology as well. So that app is a toy, and it's not where you're going to go to solve your problem. I'm sorry, because it would be nice, but that's not how it works. Okay, so let me come back here. Parallel computing paradigm is that, we start off and we have multiple cores on our desktop, and so we try to take advantage of those and use parallel enabled functions here to either use my core, or if I have one, a GPU. And it basically runs MATLABs in parallel in the background, and then they report back to me. The same thing will work from my laptop if I'm connected to a cluster or a cloud with MATLAB Parallel Server. And then basically what I do is I still prototype on my desktop or laptop, and then when I'm sure it's running on a small version of the problem, I send it up to the big infrastructure there and have my big proper problem solved up there. And you can access it directly through MATLAB. And you don't really have to change your code. You just have to change where it's going to be running the parallel stuff. And there's a lot of good information in the documentation and examples for how to do that. Okay, another thing that you can do, sometimes you have some problem that you're trying to solve, and you want to generate some code for it that can be run perhaps outside MATLAB. And we can generate C or C++ code using MATLAB Coder product for algorithms that are developed using these functions. And we will expand that list over time. If you have anything in particular that you're looking for, please let us know. And if you contact technical support about it, they will make sure that the developers know, and it will go on a list and help the prioritization there. And you can apply to a variety of different kinds of hardware platforms from the portable C and C++. Here's a bunch of resources if you want to learn about different sorts of things in optimization. There's a bunch of resources. And I want to go through and tell you just a few key takeaways again, that you can solve a wide variety of optimization problems in MATLAB, both linear, nonlinear, continuous, and mixed integer, smooth and non-smooth. And I'm going to interrupt myself right now to say, if you have any final questions, now would be a really good time to put them in the chat as I'm finishing up here, so that we have some questions ready to go. Back to the key takeaways now. We can find better solutions to multiple minima and non-smooth problems using global optimization techniques. In other words, for non-convex problems. You can use symbolic math for setting up problems and automatically calculating gradients. You can use parallel computing to speed up optimization problems. You can use C and C++ code generation to deploy optimization algorithms, and you can take advantage of the new automatic differentiation that's available in Optimization Toolbox to solve problems there. There's also a really broad MATLAB community with a lot of resources that you might use if you're having some issues or if you want to get some more information, all on the MATLAB Central community pages. And we also have a training course for those of you who are at an organization, for example, maybe a campus-wide license organization at a university. You may already have access to these trainings for free as part of the way your university set up your license. You may have access to these already. And with that, I am ready for some questions, but let me just finish one more thing. I want to really thank you for spending time watching today, and if you've been with me at all in the previous weeks. We put some links below into the YouTube page, and I want to point out 2 events in particular that you might find useful. One is a link for the MATLAB Expo 20 on demand, and it's a site that features technical talks covering a very broad range of topics where MathWorks products are central to the solutions of problems. And the second thing is, if you're interested in learning more about Simulink, now would be a great time to consider entering the Simulink Student Challenge. And if you ended up being the lucky winner, you might win $1,000. Please don't forget to subscribe to the MathWorks channel to get reminders for new events as well. And with that, I want to thank you very much for spending time and hope you enjoyed it and learned a lot. Thank you so much. Bye-bye.